wasn't bad, but it could have been better. Ow. It's hard.
That's fair.
It might be good to like figure out something. She's fun with
Okay, folks, let's go ahead and get started with today's information. Today, what we will be covering is going to be buffers. First thing you need to know about a buffer is that a buffer is a solution. Oh. Thank you. Of a weak acid, conjugate base pair. Or, I mean, technically, if you wanted to say it, it could be a solution of a weak base, conjugate acid pair. The big thing to note is you got to have solutions that are weak. It does not occur with strong acids, strong bases. It only occurs with a weak acid conjugate base pair system. Buffers are solutions that resist changes in pH. So when you have, for example, the blood buffer system is around a pH of 7.4. The blood buffer system resists changes in its pH, so that because if you go too acidic or too basic, you can wind up basically killing yourself. So it's designed to maintain a specific pH. And it's going to maintain that specific pH until it reaches its capacity. Thankfully, in our bodies, that takes quite a bit. And our bodies are continually regenerating that buffer system. So an example of a blood buffer system would be a solution that is 0.100 molar in nitrous acid and 0.100 molar in sodium nitrite. The reason that this is a buffer system is, number one, that sodium nitrite, because it is a ionic compound that contains sodium, is completely soluble in water, and it makes sodium ion and nitrite ion. So what you really have in solution is the conjugate acid-base pair of nitric acid and nitrite. Now, we're going to talk about working with this mathematically. The first thing you're going to see me typically do is I am going to write the acid dissociation reaction. The next thing you're going to see me do is, for the initial concentration, it will be the concentration of the conjugate acid-base pair. The next thing you will see happen when we start actually working with these buffers is, I should say, the thing that you need to remember is that acids react with bases. Always. What that means is if an acid is added to a buffer, the acid will react with the base, with the conjugate base pair. Compare that to if a base is added to a buffer. The base will react with the weak acid. This is going to lead us to C in our rice table. How does it change? And then finally, we will, as always, obtain E in the rice table because we are talking about a weak acid base pair. It is this E in the rice table that we use for calculation purposes. And the calculation we're going to do is going to be the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is pH is equal to the pKa plus the log of the base over the acid. Okay. So let's actually see this in use. And you will be given the Henderson-Hasselbalch equation on the exam. Okay, let's just start out. Let's go back to the problem I gave originally, which is the solution of 0.100 molar nitrous acid and 0.100 molar of sodium nitrite. Let's start by determining the pH for this buffer solution? Okay. To get to the pH of a buffer, again, we're going to use the Henderson-Hasselbalch equation. pH is equal to the pKa plus the log of the base over the acid. We know our base concentration, that is 0.100 molar in nitrite. We know our acid concentration, that is 0.100 molar in nitrous acid. We need to know our pKa in order to be able to use this equation. So nitrous acid, if you look up the Ka of nitrous acid, it is 4.6 times 10 to the minus 4. Just like with everything else, if you are given this lowercase p preceding it, it means the negative log. So we can calculate the pKa. The pKa is going to equal the negative log of the Ka. So our pKa equals negative log of 4.6 times 10 to the minus 4. And it's going to be somewhere between 3 and 4. And it's 3.34. Now we have the information we need in order to calculate the pH. The pH is going to equal the pKa of 3.34 plus the log of the base, which was 0.100 over the acid of 0.100. So in other words, the pH in this case is equal to the pKa because the log of 1 is 0. Yes.
You're finding Ka, why did you use HNO2? Not.
You all, so the Ka is always for the acidic form. And the acidic form in this case was HNO2. Also, you wouldn't have found nitrate or nitrite. You wouldn't have found a Kb for nitrite, so you had to use the nitrous acid. Okay. So if all I have is a buffer system at 0.1 molar weak acid conjugate base, this buffer system has a pH of 3.34. But a buffer system is there to resist the change in pH. That's what a buffer is there to do, resist the change in pH. So let's look at what would be the pH if 0.03 molar hydrochloric acid is added to a 0.100 molar nitrous acid, 0.100 molar nitrite buffer. Okay. This is where you start with these directions I gave you. We're going to write the weak acid dissociation reaction for the buffer. For the buffer, that is HNO2, is going to react with water to form NO2 minus and H3O plus. Initially, we had 0.100 molar of nitrous acid and 0.100 molar of nitrite. Which would be the I that I gave you in those previous directions. Now the C, the change. This is where you have to remember that acids react with bases. So since I'm adding hydrochloric acid is going to react with the base in the buffer. If it reacts with it, when you add a strong acid or a strong base to any reaction, it is going to drive the reaction to completion until somebody gets used up. So let me repeat those couple of things. Number one, acids react with bases. Number two, if you add a strong acid or a strong base, the reaction is going to go to completion until somebody gets used up. So, using those two pieces of information, let's look at this hydrochloric acid. We are adding an acid. The acid has to react with the base. Since 0.03 is lower than 0.100, we are going to use up 0.03 of that base. Now, if you are reacting with the product side and losing product, that means you have to gain reactant. So whatever you do to one side, you do the opposite to the other side. So we're going to gain 0.03 molar of nitrous acid. So that at equilibrium, you have 0.130 molar of nitrous acid, and you have 0.07 molar of nitrite. Now, we can calculate the pH because the pH is going to equal the pKa plus the log of the base over the acid. pH is equal to the 3.34 that we had previously, plus the log of the base. Well, now it's 0.07 over the acid of 0.130. When you key that into the calculator, that changed the pH to 3.07. Yes.
Why did you subtract the concentration of the 0.03 from the nitrite?
Because an acid always reacts with a base. Out of these two, the nitrite is the base. So if you're adding hydrochloric acid, it had to react with that base. So that's why I subtracted out the 0.03 from the base, is because the acid has to react with the base. So key points. Number one, the reaction. And I know I keep repeating myself on this. Buffers can be, I've seen them be challenging. So I'm trying to repeat myself to make sure that we're following along. R, the reaction I always will write is the acid dissociation reaction. This goes back up to the points that I've already written. I, when you have a buffer, it will always be the concentration of the weak acid base conjugate pair. So the weak acid conjugate base pair will always be your I. It's the C that is the most challenging, because the C represents how we are disturbing the buffer. When you are disturbing a buffer, you have to remember that an acid always reacts with the base. In this case, I added an acid, so it had to react with the base form of the conjugate acid base pair. Whatever you do to one side, you do the opposite to the other side of the reaction.
Do you always subtract it like from the
I always subtract whatever is. So in answer to your question, do you always subtract? You always subtract the disturbance. Whatever did the disturbance, that's what's getting subtracted.
For example, if this were to be a base added to this, you would add to the nitrous.
Correct, and I was going to do that there just a minute. And then at equilibrium, we simply add them together. We do our normal I, C equals equilibrium. And then you use the Henderson-Hasselbalch at equilibrium. So let's look at what would be the pH if 0.05 molar sodium hydroxide was added to a 0.100 molar nitrous acid, 0.100 molar nitrite buffer. Yes.
Will it always be?
No, I'm using that, and we'll do another example here in a minute with a different acid base pair. But the key is it will always be a weak acid conjugate base pair. So it has to be weak. That's the big key to it. It can't be a strong acid base pair. You'll always be given the Ka, or in the case of a homework, you can look up the Ka. But on a test, you'll always be given the Ka of the acid. Okay, so rice, start with the reaction of the conjugate acid base pair that is making up the buffer. So nitrous acid plus water goes to form nitrite plus hydronium. It's the initial concentrations of your conjugate acid base pair that make up the buffer system. C is the most challenging. In this particular case, I am working with sodium hydroxide. Sodium hydroxide is a base. A base reacts with an acid. So it is going to react with the acid in the buffer system. So we're going to lose 0.05 of the acid. Whatever you do to one side, you do the opposite to the other side. So at equilibrium, we'll have 0.05 of the nitrous acid, and we'll have 0.15 of the nitrite. pH is equal to the pKa plus the log of the base over the acid. So pH is equal to 3.34 plus the log, was it 3.34? Yeah. Plus the log of the base, 0.15 over the acid, 0.05. So our pH comes out to be equal to 3.82. You should double check to make sure that your pH makes sense. If you go back and to the previous example, when I added an acid, the pH became more acidic than the pKa. When I added a base in this last example, the pH became more basic than the pKa. I didn't say base, I said more basic. Questions? Okay. Then let me give you one to work with. A buffer solution was prepared by combining zero point zero 0.05 molar benzoic acid with 0.150 molar sodium benzoate. A, what is the pH of the buffer system? B, what would be the pH of a solution if zero point zero 0.03 molar KOH is added to the buffer solution? And C, what would be the pH of a solution if 0.09 molar HCl is added to the original buffer? The Ka, I should say the Ka for benzoic acid is 6.5 times 10 to the minus 5. And I'm going to let you work on it. See how it goes. In the last 4 minutes, let's see how it is going. So in part A, I asked you to determine the pH of the buffer itself. pH is So we had 0.05 molar of our benzoic acid, and we had 0.150 molar of our sodium benzoate, which is the main thing there is benzoate, because sodium is just a spectator. That's all it ever will be, is a spectator. So we did the pH is equal to the pKa of the log of base of the acid. Well, the pKa is the negative log of that Ka I gave you, which comes out to be 4.187, is equal plus the log of the base, which is 0.15 over the acid of 0.05, and it gave you a pH of 4.66. I intentionally made them different concentrations because your buffer doesn't have to be the exact same concentration of each. Yes.
Why did you not make 4.1 instead of 4.9?
If you did, we'll be close in numbers and I will still give it to you. No, I think it's because I looked at where I want to say it is due to the fact that when I looked at it, 4.187 seemed to be a good cutoff because the next number was a 0. Part B, we started out with our benzoic acid and our sodium benzoate again. We had 0.05 of the benzoic acid. We had 0.15 of the sodium benzoate. This time, we were adding 0.03 molar potassium hydroxide. Potassium hydroxide is a base, so it reacted with the acid in the reaction. Whatever you do to one side, you do the opposite to the other side. So we lost 0.03 of the acid to leave 0.02. We added 0.03 to our conjugate base for 0.180. Plug that into the Henderson-Hasselbalch, and you got a pH of 5.14. In the last one, we started with our reaction. We started with our buffer concentrations. In this particular case, you were adding 0.09 molar hydrochloric acid. Acids react with bases. So we had to take and react that 0.09 molar hydrochloric acid with the base in the reaction. So we lost 0.09 molar from the benzoate. We do the opposite to the benzoic acid, so we gained 0.09 molar. So we had 0.14 molar of our benzoic acid and 0.06 molar of our benzoate that we plugged into the Henderson-Hasselbalch to get a pH of 3.82. Any questions? On Monday, there is a tiny fraction more to discuss about buffers, but then we're going to get into titrations. And we're going to specifically focus on the steps involved in doing the calculations associated with the titration. Some of the things that we've been discussing about buffers, acids, reactive bases, is going to be things that we're using in the titration as well. And we're only going to do one type of titration on Monday. We'll do another type of titration on Wednesday. And then we should get into, then you have your test next Friday. I almost have the blackboard. I mean, if you look, you're going to find blackboard, but I haven't quite completed it yet. I still need to go and tell you what to study for on the test, but I will try to get that done by Sunday at the latest. But basically, it's going to start with acid-base chemistry. So everything since Le Chatelier's principle is on this test. Okay, I will see you on Monday.